Hello Gems! Welcome back to another video. In this video, we'll be discussing the previous year BITSAT questions from the chapter of rotational motion. Now, just a quick update, we have already finished the A series, which is the previous year question series for BITSAT. You can check out the links to that in the description box of this video. Okay. Now, our strategy is that in the next 2 months, which is March and April, we are going to complete this FAQ series. We'll try to complete this FAQ series in March and April, and in the next 2 months, which is May and June, the last 2 months before our BITSAT. Okay, so that time we are going to practice a lot of mock tests. Okay, so that is our strategy. If you want to join me in this grind, consider subscribing. That's all what I want to say. Let's begin with this video. So before we dive straight into the questions, let's briefly discuss the topic weightage for this chapter. Okay, and let's see which topics are more important as from a BITSAT point of view. Okay, so rotational motion in itself is a very important chapter for BITSAT. All the mechanics chapter are important, and rotational motion is of course one of them, and you can at least expect 2 to 3 questions directly from this chapter in the BITSAT paper that you are going to answer. Okay, so let's see which topics are important. So as you can see, only one question was asked from the topic of center of mass. Now these are the past 15-year trends. Okay, past 15-year trends of BITSAT. Okay, so only one question from center of mass, and that too it had to do with the discrete mass systems. Just use the formula m1r1 plus m2r2 upon m1 plus m2. Okay, so that type of a question. Then angular momentum, 3 questions were asked from this topic. These questions were more general, theoretical, conceptual, and having to do with your conservation of angular momentum. Now next topic is moment of inertia, BITSAT's favorite topic from this chapter, you can say. 6 questions were directly asked from this topic. Okay, these questions varied a lot. It had every concept of moment of inertia, your parallel axis theorem, perpendicular axis theorem, then some general moment of inertia questions. Okay, so the questions varied a lot. Okay, so everything was touched in moment of inertia, I can say that. Okay, so next topic is torque. From torque, only 2 questions were asked, and these questions were directly formula based. Okay, either you were asked to use torque equals r cross f, or maybe just use the formula. Okay, I alpha, something like that, formula based questions. Okay, then only one question on rotational kinetic energy, which is half I omega square. Then we have rolling, and in rolling, if you see, 6 questions were asked directly from rolling, and in rolling also one topic is very much favored, which is your rolling on an inclined plane. Okay, and in that too only one formula, will come to that. So yeah, from rolling 6 questions were asked, and most of those were based on rolling on an inclined plane. Okay, so next we have toppling. In toppling, 2 questions were asked, and yeah, they were based on simple direct conceptual questions from toppling. Okay, and 3 or more or few questions from topics other than that. Okay, so this is the weightage for our rotational motion. Okay, and let's try to practice questions based on these topics now. So questions based on center of mass over here. Now I told you that the question that was based on center of mass in BITSAT was based on the discrete mass system, which is easier to handle. You just have to use the formula m1r1 plus m2r2 upon m1 plus m2. So those type of questions we'll not discuss today. It's just simple formula based. Now we'll discuss questions that I saw in the sample paper, which were based on finding the center of mass, the coordinates of the center of mass of a system wherein you remove a certain area from that system. Okay, you'll get to know what I'm speaking of. So here we have question 1. In this question we have a circle of radius a. Okay, so from this circle we are going to remove a smaller circle of radius a by 2. Now you are supposed to tell what will be the coordinates of the system. Okay, the system means once you have removed the smaller circle from the bigger one. Okay, now this also has a simple formula, which is xcom is equal to a1 x1 minus a2 x2 upon a1 minus a2. Okay, so x coordinate of the center of mass will be given by this formula. Similarly, y coordinate will be a1 y1 minus a2 y2 upon a1 minus a2. Okay, Now A1 and A2 stands for the areas. A1 will be the area of the bigger circle over here, and A2 will be the smaller area. Okay, A2 is basically the area that is removed. Okay, and x1 is the x coordinate of the center of mass of the bigger area. Okay, listen it carefully. And x2 is the center of mass of the area 2. Okay, so let's picture that. So we have we'll break this into two areas. So first is the bigger area, the bigger circle. Okay, and then we have the cutout piece, which is this one. Okay, so it's like this. Okay, so this is the original circle and this is the cutout piece. Okay, so if we had the original circle, where would be its center of mass? Its center of mass would be, of course, at its center, right? So here, okay, so here they have told us that O is the center of this circle and it is also to be considered as the origin. Okay, so here the points are 0, 0. Okay, so if we had the bigger circle, okay, without the cutout piece, okay, then it's the coordinates of its center of mass would be at 0, 0, the origin, right? So 0, 0. So these are x1 and y1, right? These are the coordinates of center of mass of the area 1. Okay, and now coming to area 2, the cutout piece. So in this case, again the center of mass will be at the center, right? At the geometric center of this circle, but you have to measure distances from the origin, right? So if you see this distance, right, it is a by 2. Okay, so on the x-axis the distance is a by 2. Okay, the point lies on the x-axis, right? This is the x-axis, the point lies on the x-axis, so y coordinate is 0. Okay, so a by 2 comma 0 are the coordinates of your are the coordinates of center of mass of the second area. Okay, these are the coordinates of the center of mass of the first area. These are the coordinates of the center of mass of the second area. Okay, now just substitute in the formula. So a1 is the area of the first one, which is pi a square. X1 is 0. Okay, fine. A2 is the area of the smaller circle, so pi a square by 4. Okay, a by 2 the whole square, so pi a square by 4. X2 is a by 2. Okay, and a1 minus a2, so pi a square minus 1 minus 1/4. Okay, so that will be 3/4. So 3 pi a square by 4. Okay, so pi a square, pi a square, pi a square can get cancelled. This is anyway 0, and we'll have minus a by, so 4 and 4 can also get cancelled, minus a by 6. Okay, so minus a by 6. So the x coordinate of center of mass, okay, we'll write it this way, and the y coordinate of center of mass. So here we'll have x coordinate as minus a by 6. Okay, so where will we have the x coordinate? Somewhere over here, right, minus side. Okay, and a by 6, so somewhere over here. Okay, so here is the x coordinate, right? It also makes sense. When you remove this area, the center of mass will shift to the heavier side, right, where there is more mass. Okay, so if you see, once you cut out this piece, there is more mass on the left hand side, so the center of mass will shift on the left hand side. Now for YCOM, you'll again use a1 y1 minus a2 y2 upon a1 minus a2, and if you see y1 and y2 are 0, right, so of course this will be 0 and you'll get YCOM at the same place. Okay, okay, so it will be 0 again. Okay, because if you see about this axis, it is symmetric. Okay, so anyways, the point won't shift this way, the center of mass won't shift this way, since the point since the mass from the right side is removed, the point will shift to the left. Okay, but along this axis, if you see, this is symmetric, this mass is symmetric, this mass removed is symmetric, so the point won't shift this way. Anyways, you can say it through the formula too. Okay, so the coordinates of center of mass are minus a by 6 comma 0. Okay, so if you didn't understand it, let's do it once more. Okay, so here also we have a square of area of side 2a. Okay, from this we are going to remove a smaller square of side a. Okay, now this is considered to be the origin. This point O is considered as origin. You are supposed to tell the coordinates of center of mass. Okay, so again XUOM will be a1, and let's directly substitute now. A1 will be area of the bigger square, so we have, let's picture it first. So we have the bigger square 2a, okay, and the smaller square a. Okay, so bigger square area 4a square, right? Side square basically, so 4a square. X1, the x coordinate of the bigger area, so of course it will be at the center of this square, right? Now you know that this is taken as origin. Take care that this is the origin. The center of the square is not the origin this time. Okay, so this is the origin. Where is this point? If you see it, it is at the half of this length, right? Half of this side. So it will be a comma. Here also it is half of this length, right? Half of this length again a. So a comma a. This point is a comma a. If this total length is 2a, here it's a. Okay, so distance from the x-axis a, distance from the y-axis is also a. So a comma a are the coordinates of the center of mass of the first area. Okay, so x1 is a minus area of 2. This is a1 x1 minus a2. a2 is a square, side square. Okay, this square, and then x2 center of mass, or the x coordinate of the center of mass of the second area. Okay, second area, if you see, we have it over here. The center of mass will be at the center of this square. Okay, so this point we have to find. So that will be, if you see, this is a, right, and this is again a by 2. Okay, this is again a, and half of that is a by 2. Okay, so a plus a by 2, that is 3a by 2. Okay, that will be the y coordinate. Here also similarly a plus a by 2, that will be 3a by 2. Okay, so the x coordinate of the area 2 is 3a by 2. Okay, a1 minus a2, so area a, my area first minus area second, that is 3a square. Okay, so a square we can cancel out throughout. Okay, so 4a minus what is that, 4a minus 3a by 2 upon 3. Okay, so let's simplify that further. That will be 5, this will be 8 minus 3, 5a by 6. Okay, yes, the x coordinate is 5a by 6. Okay, similarly you can find the y coordinate, that will be a1 y1. So if you see, the x and the y coordinates are the same, okay, in both the cases. So the same story will go, and again the answer that you'll get is 5a by 6. Okay, so basically RCOM, okay, will be 5a by 6 comma 5a by 6. Okay, so this is how you solve such type of questions. I hope it was simple. You just have to use this formula. X1 x2 stands for the coordinates, okay, the coordinates of the center of mass of the respective area. Okay, so that is how you solve such type of questions. Let's move to our next topic now. Question number 1 and 2 from moment of inertia. In question 1 we have a square lamina. Okay, so here you are given an axis along the diagonal, okay, and the moment of inertia along this axis is I dash. You also have another axis which cuts the your square symmetrically, you can see. Okay, so that along that axis the moment of inertia is I. You are supposed to tell what is the relationship between I and I dash. Okay, it's actually very simple. First let's picture this. I'll use this book. Okay, so one, picture this as a square. Okay, square lamina, yeah, although it's not, it's rectangle. Anyways, so one, we have this axis along the diagonal, and second is this one. Okay, so which cuts the square into symmetrical pieces, right? So I can use the perpendicular axis theorem. First of all, I'll imagine two axes over here. So first is this figure. Okay, pay attention over here, and the second figure is this one. Okay, the two diagonals. Okay, of course all this axes are in the plane of the figure. Okay, they are in the plane of the figure. Okay, not perpendicular to the plane. Okay, so they are within the plane of the figure. Okay, inside this. Okay, so the this axis is along this in the plane, and this axis is like this. Okay, so now we have imagined this two axes. Okay, so here you know that the moment of inertia along this axis is I, it's given, and since a square is very much a symmetrical figure, here also the moment of inertia will be I. Okay, now according to perpendicular axis theorem, you'll know that the sum of these two i's, okay, so I plus I, the sum of the moment of inertia about two perpendicular axes in the plane is equal to the moment of inertia okay, about an axis which is perpendicular to the plane and also mutually perpendicular to the remaining two perpendiculars. Okay, what do I mean? So the sum of the moment of inertia about this axis and this axis will be equal to the moment of inertia about this axis. Okay, so that is what I mean. Okay, and I and I are equal because square is symmetrical. So 2I equals I perpendicular. Okay, and similarly, let's apply the logic over here. The sum of the moment of inertia. Now these are diagonals. So in a square, the diagonals bisect each other perpendicularly. So this also are two perpendicular axes. Here also it's two perpendicular axes. Okay. So here also the sum of the moment of inertia, here it will be I dash, and here also I dash, because square is symmetrical. So I dash plus I dash will be equal to I dash plus I dash will be equal to sum of the moment of inertia about the perpendicular axis, right? It will be equal to the moment of inertia about the perpendicular axis, not the sum. So 2I dash will be equal to the moment of inertia along the perpendicular. Okay, so in both the cases, if you see this case and this case, the sum is finally equal to the perpendicular, right? The moment of inertia about the perpendicular to the plane. Okay, so you can equate this two. Okay, right? So from equation 1 and 2, you can see the right hand side is the same. So you can equate this to 2I equals 2I dash, or I equals I dash. Okay, it's actually very simple to see that the moment of inertia about this two axes will be the same. Okay, so I hope the approach was simple. We just used the perpendicular axis theorem. Okay, so we imagine two axes like this and two axes like this, and we know that their sum will be equal to a certain quantity. Okay, moment of inertia about the perpendicular. Okay, like this, moment of inertia about this axis. Okay, and so since their sum is equal to that, we equated this, and you can cancel the twos, and you'll see that the moment of inertia about this is same as the moment of inertia about this. Okay, so yeah, option A is the correct choice over here. Okay, now in question 2 we have a ring which is rotating. Okay, about an axis which is perpendicular and passing through its center of mass. Mass is given as small m. Its initial angular velocity is omega. Now you are going to attach 2 point masses which are capital M and capital M each on the opposite sides. Okay, so you are supposed to tell what will happen to the angular velocity. Okay, you'll attach it gently, and what do I mean by gently? Gently just means that there is no external torque applied. Okay, so you can in fact use your conservation of angular momentum, right? So why is this a question of moment of inertia? Because most of the time we are going to find this I dash. Okay, although we are using conservation of angular momentum, our main motto over here is to find I dash. Okay, so if you see I is the moment of inertia, this is the initial system, right? And this is the second system, right? So I is the moment of inertia of this, omega is the omega is the angular velocity of this, omega dash is the angular velocity of this, and I dash is the moment of inertia of this system. Okay, now omega dash, now from here we want omega dash, right? So it will be given as I upon I dash into omega. Now I dash, how can we find I dash? Okay, I dash, if you see, we have to find the moment of inertia of this system, right? So first of all, it will be the moment of inertia of the ring, which is m r square, m small m into r square, right? And then we also have to account for this point masses which are at a distance of r from the axis, right? So these are point masses, so you can directly add the moment of inertia, right? Moment of inertia for your purpose is a scalar. Okay, so mr square plus mr square, right? So mass times their distance from the axis, mass times their distance from the axis. Okay, so m small m r square plus capital M. Now capital M r square, capital M r square, that is 2 capital M r square. Okay, so this is I dash. Now just substitute I dash over there and you'll have your answer. Now what is I? I, you can simply see it as mr square, right? In the first case, what is the moment of inertia? It's the moment of inertia of a ring is mr square, right? So mass of the ring times radius square. So here we have to substitute I, which is mr square, upon I dash, which is m plus 2m into r square. Okay, I have taken a r square common, and omega, yes, omega is itself omega. Yes, angular velocity in the first case, it's omega. R square and r square will get cancelled, so we have omega m upon m plus 2m. Okay, omega m upon m plus 2m. Option C is the correct choice over here. Okay, so used conservation of angular momentum, found this I dash using, yeah, simple logic of moment of inertia, and I is simple, we know it, and just substituted over here and we have our answer. Okay, so let's do few more questions on moment of inertia now. So question 3 and 4 over here. In question 3, you are given a disk. You are supposed to tell what is the ratio of moment of inertia about this axis to moment of inertia about this axis. Okay. Now it's actually very simple. The IZ. Okay. Now this two axes are perpendicular to the disk. Okay. Perpendicular to the plane of the disk. So the disk is like this, and the planes are like this and like this. Okay. So Iz will be simply mr square by 2, right? It is passing through the center of mass, through the center of the disk. So it is mr square by 2, right? The moment of inertia about an axis perpendicular to the plane of the disk and passing through the center of mass is mr square by 2. Okay. Now what about Iz dash? Now some of you might directly know it by heart, but I don't. So let's use the parallel axis theorem. Okay. Now what does it say? So the moment of inertia about a parallel axis will be equal to the moment of inertia about an axis passing through the center of mass, so which is this one. Okay, and total mass times the distance between the two axes, which is basically r, if you see the radius of the disk. Okay, so that is r. So mass times the radius or the distance between the two axes. Okay, so total mass times the distance between the two axes, which is r. Okay, now Iz we know it as mr square by 2. So here basically mr square by 2 plus mr square, 1 plus half, which is 3 by 2, right? 1 plus half, 1 and a half, 3 by 2. Okay, so now you can easily take the ratio. You will see that Iz is 3 times this, right? So Iz by Iz dash, so this is 3 times of the first one. Okay, so it is 1 is to 3. Okay, so the ratio over here is 1 is to 3. Quite a simple question. Here is a complex one. Now you are supposed to find the moment of inertia of the system about this axis. Okay, these are disks. Okay, all of these are disks. Okay, each of them have mass m and radius r. Okay, so here we have disk 1, here we have disk 2, and here we have disk 3. Okay, so first of all, the moment of inertia will be due to this disk first, right? This disk, right? So that is mr square by 2 due to that disk. Now we have these two disks as well. Okay, and they are symmetrically placed, right? They are symmetrical about the axis, you can see. So I can consider only one disk and multiply its moment of inertia by 2. Okay, so that is what I'm going to do. So I'll multiply the moment of inertia of this particular disk by 2. Okay, now let's find the moment of inertia of this disk about this axis. Okay, so we have this disk and we have this disk. Okay, we have to find moment of inertia about this axis, right, for this disk. Okay, so let's see. First we can find the moment of inertia about this axis I dash. I dash, if you see, is the axis which is passing along the diameter of that disk, right? So we have this disk over here. Okay, first disk over here, second disk over here, and the I dash. Okay, so if you see, this axis is passing along the diameter of that disk. Okay, so in that case, what is the moment of inertia of a ring along the diameter? It's mr square by 4. Okay, please remember that. So I dash will be nothing but mr square by 4. Okay, but it is the moment of inertia about the diameter, not this axis. We have to find the moment of inertia about this axis. Okay, you can see that the two of them are parallel, right? So we can use the parallel axis theorem over here. Okay, so the moment of inertia about this axis, okay, we'll name it z. Okay, so I z will be given as moment of inertia about this axis, which is mr square by 4. Okay, I dash. Okay, so I dash plus the total mass of this disk, m, small m, right? And times the distance between the two disks, right? So it is at the radius distance, right? This disk is at a radius distance, so mr square. So this will be 5 by 4 mr square, right? Now this is for one disk, right? This is the moment of inertia about this axis for this disk. Okay, I repeat that. This is the moment of inertia for this disk about this axis. Okay, so yeah, this is for one disk. We have the other disk too, so we are multiplying 2 with this. Okay, so mr square by 4. Okay, so mr square by 2 plus this and this will get cancelled. 5 mr square by 2, which is 6 mr square by 2, again 5 plus 1, right? So that will be 3 mr square. It will cancel and we get 3 mr square. Yes, option A, 3 mr square is the correct choice over here. I hope you are able to understand it. If you are confused a bit, you can rewind the video and watch it again. Okay, so basically we found the moment of inertia. First, this is due to this disk, okay, and then we have two disks, so we multiply 2 with the moment of inertia for this disk about this axis, okay, and we found that using the parallel axis theorem. Okay, so that's all from moment of inertia, I guess. We'll now move to torque and angular momentum. So question 1 and 2, now these questions are from torque and angular momentum. Okay, these two are from torque, and I told you that the questions that were based on torque were very straightforward, right? They were just formula based questions. So here also we'll practice some formula based questions. Okay, either you have to use R cross F or a simple formula of torque. Okay, so let's see. So first one, we are given the torque, the value of torque. Okay, and we are told that certain force of 1 Newton acts on this particle at an angle theta. Okay, now this is the point about which torque is found out. Okay, we'll call that origin, and it is at a distance of 5 meters from your particle. Okay, you are supposed to find this angle theta. Okay, now it's very simple. Torque equals R cross F, or I can write it as RF sine theta, right? So torque is given as 2.5. R is the distance, okay, of the point P. If you see, it's 5. Okay, fine. And then F is 1 Newton sine theta. Okay, and here from here 2.5 and 5, that will give you half, right? And here you have sine theta. Okay, 2.5 2 is 5. Okay, so sine theta is half, and so that means theta will be 30 degrees or pi by 6. Okay, so option C, pi by 6 is the correct choice over here. Okay, pretty simple question over here. Let's come to this question now. Okay, here you are supposed to find torque about 1 comma minus 1, and here you are given the force vector. Okay, so find the torque vector. Okay, first of all, you can write the r vector as x I cap plus y j cap. Okay, this is how you write the position vector. If there was z, you'll write plus z k cap. Okay, so x is the x coordinate 1, so 1 I cap, so that is I cap, and y is minus 1, so minus 1 j cap. Okay, so minus j cap basically. Okay, so we get the r vector over here. So this is how you find a vector from the coordinates. Okay, the position vector from the coordinates. Now torque, you can simply write it as r cross f, right? So you have to find the cross product of this. R is I cap minus j cap, and you have to cross it with minus f k cap. F is like a number, okay, just like here we have 1 and minus 1. F is also a number which is not given. Okay, so now we'll have to remember this I cap, j cap, I hope you know this, k cap. Okay, so this is useful in cross product. Okay, so first we have to multiply this with this, so this and this we have to cross, so we'll get minus I cap cross k cap. Okay, and if you see minus, so I cap cross k cap, I cap cross k cap, so you are going in the opposite direction. This direction is positive. Okay, if you go in the opposite direction, okay, I j k. Okay, so if you go in the opposite direction, you will get negative. Okay, and negative, so I cap cross k cap will be j cap but negative j cap because we are going in the opposite direction. So we'll have minus j cap, okay, and this minus sign, and we'll have j cap cross, okay, this and this minus sign will cancel, okay, and we have also f, okay, f, and forget that f k cap, right? So I cap cross k cap, and we also have an f, okay, not to confuse you, I'll do that again. Okay, so we'll multiply it. So minus f I'll take common, okay, and then we'll have I cap cross k cap, okay, and then we have, again we have to multiply this with this one now. So minus and minus will make it plus, f I'll bring it out, okay, and I can write j cap cross k cap, okay, order is important, so j cap cross k cap, okay, not k cap cross j cap, you'll get the sign wrong, okay. So if you do that, so order is important, I cap cross k cap, okay. Now I cap cross k cap, you can see that it will give you j cap, but j cap it is going in the opposite sense, right? Clockwise is positive and this is negative. If you go opposite, it is negative. So minus j cap, this will give you minus j cap. So f, and this minus sign will neutralize with it. So f j cap, and here you'll get j cap cross k cap. So j cap cross k cap will give you I cap, and it's in the same direction, so positive. So f I cap. Now you can take f common from here, and you can write it as I cap plus j cap, okay. So option C, F I cap plus j cap is the correct choice over here. Okay, so simple rules of your cross product you were supposed to use over here. Okay, and the formula R cross F. Okay, so those were simple questions from torque. Let's do one more question which is based on conservation of angular momentum. Questions from rolling. Now in rolling, only one topic was very much favorite of your BITSAT, which is rolling down the incline. Questions were asked repeatedly on this topic, and we have practiced a lot of this in the A series too. So we'll just do one for demo over here. Okay, you can check out, if you are curious enough, you can check out the previous year question series towards the end of this video. Okay. Now, the only formula that we are supposed to know in this case is the acceleration formula, which is g sine theta upon 1 plus I by mr square. Okay, the letters have their usual meaning, or you can write it in terms of radius of gyration. Okay, just for a demo, this is a question from 2020, I guess. Okay, so here they asked you, you have a hollow sphere and a solid sphere of the same mass and the same radius. Okay, so the only difference is one is hollow and the other one is a solid. Okay, so who will reach the bottom first? Or you were supposed to tell the ratio of their accelerations. Okay, so either one of the questions, I don't know which one it is, but we'll try to answer both. Okay, so basically the one which has higher acceleration will reach the bottom first. Okay, so A1 will treat it as solid. Okay, solid sphere. So we have g sine theta, which is constant in both the cases. If you see, theta is same, okay, and g is of course a constant. Only thing that is differing over here is the moment of inertia. Okay, so 1 plus I for solid sphere is 2 by 5 mr square. Okay, these are the values you should know, 2 by 5 mr square. Okay, and here again we have mr square. Okay, so this and this will get cancelled, and you'll get g sine theta 1 plus, so we'll have 7, so 5 by 7. Okay, just quick maths over here. Okay, so 5 by 7 g sine theta. Let's find for the hollow one. Okay, A2 will be given as g sine theta upon 1 plus, now it will be 2 by 3. Okay, actually you could have just seen which one has a bigger radius of gyration. Okay, and then you can see the inverse relation in the acceleration. Okay, so that way you could have also done it. Okay, anyways, so the moment of inertia of a hollow sphere is 2 by 3 mr square, right? And again we have mr square, this and this will get cancelled, and here we'll have 3 by 5. Okay, so 3 by 5 g sine theta. Okay, now you can easily tell the ratio. Okay, you can take the ratio now a1 by a2, and you can easily see the answer over here. Okay, and you can also tell which one will reach first. The one with higher acceleration will reach first. So just calculate these values. This will be 3 by 5 is, what is that? 3 by 5 is 0.6. So 0.6 times some constant, and here also we have the same constant, and calculate 5 by 7. So okay, point it as 7s are okay, so this one is bigger, of course, so 0.7 something. So this one is bigger, so the solid sphere will reach first. Okay, yeah, that's correct. Solid sphere will reach first, and you can also find the ratio. Okay, so that is about this questions. Okay, you can of course check more in the previous year question series that we discussed. Let's move to our last topic, which is toppling. So question number 1 and 2 from toppling, the last few questions that we are going to do today. Okay, so here you are supposed to tell what is the minimum force F that should be applied on this block so that it just topples. Okay, now this type of questions are conceptual. Okay, if you know the concept, it's very easy to solve. Okay, you can see that when this block is just about to topple, what will be the condition? The condition will be somewhat like this, right? So the only point of contact is this one. Okay, so when it is going to just the condition is just to topple, then the normal force will shift over here. Okay, so that is the catch point over here. So the normal force will shift to the extreme right, because this is the condition that we want for the block to just to topple. Okay, so yes, so the catch point over here is normal will shift over here. Again, we have mg at the center of mass. Okay, now we'll find torque about this point. Okay, you can also find about the about your center of mass, but I don't want this friction in our discussion, and I also don't want normal force. Okay, so we'll find about this point. Okay, and you can see that this distance will be a by 2. Okay, the okay, we'll consider the side as A. What was it? Was it given in the question? Yes, it was given as A. Okay, and here the distance is A by 2. Okay, so I am considering the torque about this point. Okay, so if you see the normal reaction and the frictional force pass through that point, so the torque due to the normal reaction and frictional force is 0. Torque is R cross F, right? So R is 0, torque is 0. Yes. And if you see mg is rotating the block this way about this point, the mg is like this. Okay, so it's anti-clockwise and f is clockwise, and these two torques when the block is just about to topple, they are almost balancing each other. Okay, so the torque in the anti-clockwise direction is the same as torque in the clockwise direction, or the torque due to this force is equal to the torque due to mg. Okay, so what is the torque due to mg? R cross F, right? So basically mg into if you say it's perpendicular, so anyways rf sin theta sin 91. That is so basically you have to multiply f and r. So f is a by 2 and r is mg. F is mg, r is a by 2. Okay, so distance from the point is a by 2 and mg is the force, right? And for this one, if you see the torque, again it's the angle between them is 90 and sin 91. The force is F, and what is the distance? Distance is distance is A from the point, right? So you can easily see that the force that we require for this block to topple it is mg by 2. Okay, so mg by 2 is the correct choice over here. Okay, now again we have a question over here. Here we are pressing this block against a wall. Okay, here we are shown all the forces. This is the friction force, this is mg, this is normal reaction. Of course, the normal reaction always does not pass through the center of mass. Sometimes it shifts in order to avoid the block from toppling. Okay, and that is what is happening over here. Okay, so you are supposed to tell x in order for this block to not to topple. Okay, so the block is completely at rest. It's not in translation motion or rotational motion. Okay, so you have to find x so that the block remains at rest. Okay, so what can we do? Now we know that the block is at rest, it is in equilibrium. Okay, so we can equate n and f, right? F is nothing but 2 mg. It was given in the question. Okay, So N equals 2 mg. Okay, so these two forces are equal. That's why there is no motion in this direction. Also, this force, the frictional force and the mg force are equal. That's why there is no motion like this. Okay, so the frictional force equals mg. Okay, these two equations we were able to deduce. Now let's balance the torque. Okay, so what point can we choose? We can choose this point, of course, but there is no clear advantage that you can see. Only the frictional force will be cancelled, but the other points will not be cancelled. Okay, so I'll choose this point. Okay, so that this force will be cancelled. Okay, and normal reaction will remain, and frictional force will also remain. Okay, so yes, fine. Okay, so now again I missed out something, I guess. Okay, so this distance should be a. Let me just check that. Yes, the distance was given as a. Okay, so yes, I forgot to write it, sorry. Now let's try to solve it. Okay, we'll balance the torque above the center of mass. Okay, there is a slight disadvantage in doing about this point, although you'll get the answer, you can try it, of course. So let's do it at the center of mass. Okay, so you can balance the torque. One will be the torque due to your normal force, right? So the torque due to normal force will be same as the torque due to friction, right? Torque due to normal force is in the clockwise direction. Torque due to friction about this point is in the anti-clockwise direction. So torque due to friction. Okay, and mg, if you see, is also passing through the center of mass, of course. So it is also 0. Okay, so torque due to normal force is n times of x, right? N times of x distance from the point. Okay, and a torque due to your frictional force is the frictional force times this distance, right? This distance is a by 2. This total distance is a, and this distance will be a by 2 since it's the center of mass, right? So this distance is a by 2. Now use these relations, okay, and try to find the answer. N is equal to 2 mg, fine, and into x is equal to f is mg, okay, and the distance is a by 2. So I can write it this way. Okay, so mg and mg will get cancelled. X will be nothing but a by 4. Okay, so option a by 4 is the correct choice over here. Okay, I hope the concept was easy to grasp. If not, you can watch it again. That is the advantage of watching it online. Anyways, that's it for today's lecture. I'll see you soon in the next class. Consider subscribing, and yeah, keep enjoying physics.